Hey guys, Hudson here. Thought I would create a video for class today so that we can make sure that you learn this lesson and hopefully have time left over at the end to work on your homework. And actually I will change that to you most definitely are going to have time left over to work on your homework. So if we look at the example problem here, and of course on your notes I show you out a little bit more. Imagine that we have a red strip wrapping all these cylinders, and actually you'll see this a lot as you see cylinders being shipped or items being packaged. We're going to wrap the cylinders offset so that this cylinder won't go anywhere, and therefore this red strip can tighten down around it. We see that the cross-sectional area enclosed by the strip is 115 centimeters. The cross-section means what would be right in between there, so kind of looking at the two-dimensional area enclosed by it. So if we wanted to find what's the radius of each cylinder, what's the size of this? Say we're looking at something being shipped and we're deciding is it the right size or will this work for our current application? We can make a sketch of the cross-sectional area by looking at what it would be two-dimensionally. So to look at it two-dimensionally, we pull it out and we say, well, we know every circle has a radius of r since they're all the same. So the distances between the centers are 2r, and actually we can make rectangles that we can more easily look at the area of. And what you'll see left over is, since I have an equilateral triangle in the middle here, the remaining angles out here, once we get beyond the rectangle angle, we have 120 degrees, 120 degrees, and 120 degrees. If I combine all three of these sections, I would actually have a full circle. So if we break my shapes apart, I have an equilateral triangle, three rectangles that all match each other. They're all the exact same shape. They are congruent. And then the three third circles will combine to make a whole circle. So if I analyze the formulas for each section of that area, we see here that the triangle, since we know the area is 1/2 base times height, we have the base of the area times the height of the area, and we could work out the math to look at how we got that there. We can say that each rectangle is going to be 2r squared, and each sector will be 1/3 pi r squared, or all three sectors combined would just be pi r squared. And we can then work the math to find out that our radius is approximately 3.3 centimeters in this situation. So just a little quick warm-up to look at why are we going to use radical functions. Especially when we work with circles around objects, radicals are really important to understand. Moving on to our first problem here, we actually want to look at our notes and notice the key concept that I have listed here. So let's take a second to look at our parent functions. When we look at our parent function, we have the square root function and then the general radical function, because again, the general radical function can be any root, so we could do third or fourth or fifth. We can take the parent function and reflect it, which would just be to apply a negative coefficient on that. We can take it and stretch it or shrink it. We call this coefficient the compression factor. So that coefficient of A will allow my graph to compress or get larger. And then we can shift it either horizontally or vertically. We use K as our vertical shift because it is the constant value that is going to be added or subtracted. So if we pop over into Desmos and look at our radical graph, I have here the parent function graph, just radical x. I have A set to 1, so it won't do anything. H and K are both set to 0. So as I move my H and get larger, you'll see that as I add values, I actually shift left. As I subtract values, I actually shift right. My constant value out here, as I add a constant value, I shift up. As I subtract a constant value, I shift down. Notice that my graph has not changed size, it's just changed location. And then as I change my A, as I get bigger, my multiplier in front, I'm going to get further and further away from the x-axis because that multiplier has an effect on the y, because y will be whatever this equals. So of course as A gets bigger, my y will get bigger. And then of course as my A gets smaller or negative, it flips it over the axis. So the only real way that this gets smaller is if it's between -1 or +1, because that will compress. Otherwise, it will make my graph get further away, and then we are back at the parent function. So again, if you have any issues with looking at these graphs, you can always come into Desmos and check that out. So we want to come here and look at our graphs of radical x minus 2 and radical x plus 1, what we should know is this constant added or subtracted on the end is going to perform a vertical shift. So whether I use my graphing calculator or whether I go use Desmos, my first graph that I would like to put on here is radical x minus 2, which of course you have on your paper already shown to you. But if I change my slider to minus 2, we can see that all it did was shift my graph down by 2. So there in my notes, we would want this to say that the shift was down 2. Also, likewise, if we have radical x and we add 1, that shift is going to just shift me up 1, so I can change my k slider to a plus 1. Now, of course, if we want to use my TI calculator to do this, we have to be accurate when we plug in these values to the y equals menu. So really quickly, if you didn't have a TI, grab one and try this out. So all I need to do is go to my y equals menu, do radical x, then I close my parentheses. That's the biggest step there. If you don't close your parentheses, your graph will be completely wrong. So I'm going to graph radical x minus 2. My window can just be the standard window. So I see that shifts my graph down. If I want, I can go ahead and graph the parent function just so I can see the comparison. So there's my parent function again. And then if I do my radical x plus 1, I'm actually just going to change, instead of my minus 2, I'll just change that to a plus 1 and see where that goes. It just shifts it up 1 from the parent function. We see the distance between them is always the same because I have not used a compression factor. All I've done is shift vertically. If you try the got it on your own, we see radical x plus 2 and radical x minus 3. Take a second to decide what would happen with these graphs. And hopefully what you figured out is that the first one will be shifted up by 2, and the next one will be shifted down by 3. For problem 2, go ahead and move on to the next video.